Well, like the C is like one octave up from like that original C. Well, I guess it would be.
Ma'am, will you help me with this?
Yeah, for sure.
Why does she need to help you?
Because I'm fake.
Let's not jump to conclusions. All right, are you ready? So I need you to listen closely. So here's what we're gonna do. So take one in each hand.
Oh, okay.
And you're gonna do like boom, boom on your knee. Okay, and how do they sound? Can you hear them good?
Yeah.
All right, so here's what we're gonna do. Right, come on over. You're gonna do boom, boom, and then you're gonna go 1, 2, and I'm gonna go 3, 4. So it's like one every like second. So listen closely. Go ahead. Oh, I was slow. Let's go again. Go ahead.
Oh, that was not this. Oh, no.
Nope, let's go again.
Yeah. Oh, wait.
Nope, we're all going to the same thing. Go. How did it sound? It's a chord. Okay, does it sound good? So sometimes if you mix these letters, like I have, what do you have?
Where do I see letters? Oh, C and E.
So she has C, E, and I have G, C. Did that sound good together? All right, let's try another one. Keep your
Where
C.
did that lead?
I don't know.
Musician.
Keep your C.
You know what? I can play.
This road.
I can play C scale. Which one can I?
Are you ready?
Got it. I can
Listen closely. Don't miss it. Go ahead.
I know. I can push all this stuff.
C. Do those all sound good together?
Church.
Yes, they do. They all sound good together. Now, here's the problem. Okay? Let's do
Create a
this one.
dissonant chord. Make us uncomfortable.
So do your C. Do it nice and hard.
Nah.
That's right. Those sound bad together,
We
right?
love dissonance.
Okay. So, do tuning forks. You guys will be able to use a tuning fork probably tomorrow. Okay, probably tomorrow. Oh no, Friday. We gotta do something else.
It's gotta be a snap.
The C you use.
So,
I memorized it.
I'm definitely not gonna be here Friday.
what's going on Friday? What are you going to Chicago for? I'm sorry?
Visit my sister.
Oh, that sounds nice. What does she do in Chicago?
Teach.
She's a student teacher? Did you hurt your knees by banging them? It's all right.
They were hurting this morning. Yeah.
So, here's the question. How does the sound wave get from, let's say, me to you?
Air.
The air was through a medium.
Does it travel through the air?
Yeah.
So, we talked about this earlier in the year. We talked about how there's only two kinds of waves. Okay? There's only two kinds of waves. One kind of wave is the electromagnetic waves. True? Does that seem vaguely familiar? So, So, tell me about the electromagnetic waves. Tell me one thing we know about electromagnetic waves. Radio waves. We call it the electromagnetic spectrum. There are 6 portions or 7 portions, right? Radio, microwave, infrared, light, ultraviolet, X-rays and gamma rays, yes?
They can travel by.
They can travel through a medium, like they can travel through glass or air, right?
Or nothing.
However, more importantly, they don't need a medium to travel, right? So like, there is literally nothing, right? Once you get above the atmosphere, there's nothing there, right? There's not like space gas and dust and stuff like that. It's few and far between these things are. So electromagnetic waves do not need anything for them to travel through. That is a cool thing. Mechanical waves, on the other hand, however, do need some sort of physical matter, right? They need some sort of not only do they need some physical matter to travel through, they actually need some sort of physical matter for their very existence. Like if you want to create a water wave, what's the one thing you need? Water. You need some sort of physical matter for its existence. That's mechanical waves. So check with your neighbor, see if you can come up with some different types of mechanical waves. Check your neighbors now. Do it quickly. All right, here we go. Angelina, give me a wave type. Right? Yeah, absolutely. We call these seismic waves, right? The study of seismic waves is super important because we have all of our information about what exists below the surface of the earth from these seismic waves. Inside the earth, we think that the core, there's like a core, and then there's like an outer layer that has a different density, and then there's like the liquid hot magma, right, that has even a different density of that. So by studying the way seismic waves move through the earth, right, we get a sense of what the earth is made of. So seismic waves is absolutely a great example. Thank you very much. Yes?
I just had a question. Do you know where that earthquake originated? That one that we felt like a couple weeks ago? No, I know it was in Canada, but we're in the middle of a plate. Yeah.
Well, so sometimes, and this is probably true, so when the glacier, right, 10, 15,000 years ago, the glacier sat on us, and it squished us down a little bit, and we have occasionally very earthquakes in the area. They're due to, it's called glacial rebound.
Yeah.
So the glacier was a lot of ice, and it was pushing down on us a lot, and like over time we'll rebound a little bit. It may have been a glacial rebound. Does that make sense?
Yeah.
Give me another wave. Michaela, what do you think? Oh my lord. What?
I feel the same thing.
Go.
Shockwave,
What's a shock wave?
like from a bomb or something.
Oh, sure. Actually, this is a fine example. So, kind of. So, how does that work, right? A bomb, any kind of bomb works with this methodology. There's an explosion, right? And some gas is released at a very, very high speed. So as this gas expands, there's gases around it, right? Like there's the air around it. And so these gases right here move out. But as soon as they hit the gases around them, those gases push on the other gas particles, and this shock wave, as you said, moves outward because it's bump, 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 bump. Is that cool?
Yeah.
Awesome. Mr. Haggard, give me another one.
It's like a regular wave in water.
Sure, a water wave is a great example of a mechanical wave, right? It needs the water to exist, right? And it has the properties of waves. Good. I like it. Yes?
Sound.
Sound's a great one. Can sound move through air?
Yeah.
Because you can hear me, right? Can sound move through water?
Yes.
I mean, you can hear things underwater, true?
Yeah.
Not as well.
Right?
Not great.
If you were a dolphin, however, this would be fine for you. True?
Or like banshee.
Give me another one. Yeah.
If it moves faster like, through water, how come we can't hear it as well underwater?
So our eardrums are air on the inside, air on the outside. So they are conditioned to move through the air. Does that make sense? So what happens is in water, the vibration will hit your eardrum and cause it to vibrate. But it doesn't vibrate as well because there's water up against it. And so you don't get the true vibration as you do in air. Jordan, give me another one.
A hand wave.
Yeah, so I mean, this is more just a single vibration. But what about like if you go to a stadium? What about the wave? You ever done the wave at a stadium? Right? The wave is a really good example of this because does it take some sort of physical matter for its existence? It's the people, right? But consider this for a moment. When you do the wave, what way do you personally move? You just move up and down. But what way does the actual wave pulse go?
Direct, yeah.
It goes around. So how do we get a wave where we just go up and down that moves in its own direction. You see why that's weird? Yeah.
What about gravitational waves?
I don't know, what's a gravitational wave?
Okay. Back up, wait, from that.
What's that?
I'm gonna back away from that.
Oh. I don't know what that is.
What about light wave?
So a light wave, so we think light is a wave. Okay, we think light is a wave.
But isn't it part of the visual light from the electromagnetic spectrum?
But we got some issues because we can't see the fact that it's a wave. We just can somehow infer the fact that it's a wave. But I don't actually really know for sure.
Yeah.
I'm just tired, man.
Paul, you
So they did that earlier. It's been around. So I figured you're like,
Special little friend. All right, so I want you to watch this for just a moment, okay? I want you to watch this for just a moment. Now, what we've done is... Oh, man, one job. What's going on? So if I send it up and down, can I send a wave down that way? And we did it on the floor where if I send it like left and right, the wave goes down. Is that cool? Consider for a moment, what are you noticing? If I shake it left and right, which way does the wave go? Down and back. You all see that? So I'm going to shake it left and right, and the wave goes down and back. How is that orientation of the shake direction versus the travel direction? The shake direction is left and right, but the travel direction is down and back. Is that the same as the stadium wave, or is that different than the stadium wave?
No.
It's flipped.
it's the same, it's just you get the.
You see my question?
Yeah, we move up and down, that moves up and
Yeah,
down.
if you flip it and then
So,
rotate it.
what about this? What if I, now this is going to be a little different. I'm going to give it a little push. You see the straight push that I'm giving it? Can you see that little bunchy pulse move down and back? Can you see that thing? That's a little different because my vibration direction is the same direction as the direction of travel.
What is that type of wave called?
It's called, it has two names. It's called a longitudinal wave. It's also called a compressional wave. Do you see the difference in the similarities of these two kind of concepts there? So we're going to we should try not to hold each other's hand. Just throwing that out there. Just a general comment. Because I think that this kind of wave might be important for our study of sound. I gotta get more big plastic slinkies. I don't even know where this one's from. This looks like it's promotional. ZTD-ADIX. From the Watsu America. Oh, look, it's so interesting. It's for a phone. Like an old school, like, sit on the desk kind of phone.
Oh, nice. Is it?
Man, how old is this thing? Last thing before we go. I want you to estimate right now. We're doing it in miles per hour. Right? I start talking to you. There's a slight delay between when the sound leaves me and when it gets to you. But you don't really notice. Right? Even if I were to drop this on here, and you're watching it, you saw it hit. You saw it hit and you heard it hit really at the same time in your brain. How fast do you think sound travels?
Well, fast. Very
In miles per hour.
720.
A lot per hour.
700?
Yeah, 720.
Is that where I
What?
put
That seems ridiculous. 700?
Yeah. Well, it depends on the air temperature.